Welcome to this explainer. Think about the city you live in for just a second. You've got roads, intersections, traffic lights, and rules that keep cars from, well, crashing into each other. Now imagine the sheer chaos of that exact same city if there were absolutely no traffic lights or stop signs, just cars blindly accelerating into intersections. Complete gridlock, right? Well, the digital world, that invisible infrastructure connecting all our devices, is built on the exact same principles, and it faces the exact same threat of chaos. So today, we're going to explore the blueprint of the digital city. We're going to map out the physical layouts that form our network roads, and then we'll decode the brilliant software protocols that act as our digital traffic cups.
Here's our roadmap for the explainer. We'll start with mapping the digital world, then look at early bus and ring networks, and move into the star topology standard. After that, we'll cover the rules of the road, handling data collisions, and finish up with the channel capture effect. All right, let's jump right into section 1, mapping the digital world. Because before any data can flow, we've got to pave the roads. Okay, let's lock down this fundamental concept, network topology. It's simply the arrangement of various elements, like links and nodes, in a communication network. But it's not just about where the cables are physically plugged in. Topology can be physical, the actual real-world placement of devices and cables, or it can be logical, which is how the signals actually act on the network media to pass from device to device. Think of it like a city street. The physical topology is the asphalt road itself, drawn straight on a map. But the logical topology? That's the one-way sign at the corner. The physical road could easily handle movement in both directions, but the logical rules dictate exactly how the traffic is actually allowed to flow. And as we'll see, the physical and logical layouts aren't always the same thing. Moving to section 2, let's take a look at how engineers first try to lay out these digital neighborhoods with bus and ring networks.
So, the linear bus topology acts just like a single main street. All your nodes, the computers and servers, are connected to one central cable, usually called the backbone or the bus. When a computer sends a signal, it just broadcasts it out and it travels to all the workstations on that bus. Only the machine with the matching MAC or IP address actually accepts it. The rest just toss it out. And you have these things called terminators at the ends of the line, which are absolutely vital. Without those terminators absorbing the signal, the data would physically bounce off the end of the wire and literally echo back and forth endlessly. It would completely cripple the network with noise. Now, this setup was incredibly cost-effective, but it definitely had some severe limits.
Contrast that linear street with the ring topology. Instead of a single line with ends, the nodes connect end-to-end to form a closed loop. Data travels in one direction, and it uses this highly organized token passing system. Imagine a tiny digital baton, a token, just continuously sprinting around the loop. A computer can only send data when it grabs an empty token. Once it attaches its data, the token travels to the destination, drops off the payload, and an empty token is released back into the wild. It's incredibly orderly, and it handles high traffic volumes without any collisions. Actually, this specific architecture was heavily used by IBM back in the 80s and 90s for massive corporate networks, just because of how reliably it managed heavy loads. But here's the wild part. Despite having vastly different architectures, both of these early designs shared a fatal flaw. They both had a catastrophic single point of failure. On a bus network, if that main backbone cable breaks, the whole network goes down. And in a ring network, if just one single workstation or port dies, the loop is broken and the entire network goes dark. Imagine your whole office's internet completely crashing just because one person accidentally unplugged their computer under their desk. That was the reality of early digital neighborhoods. And man, it simply wasn't sustainable as our network started growing. So, how did we fix this? That brings us to section 3, the star topology standard. This was the big one. This was the architectural leap forward we needed, the star layout. Every single node connects directly to a central hub or switch with its own dedicated cable. In this setup, the central device manages all the network communications. It operates a lot like a highly efficient post office sorting facility. Instead of shouting a message down the entire street for everyone to hear, the switch directs the traffic specifically and only to where it needs to go. If you cut the cable to one laptop, only that laptop loses its connection. The rest of the network just keeps humming along perfectly. This isolation finally eliminated the shared collision domains that plagued the older designs. Of course, this modern layout comes with its own trade-offs. Because every single device needs a home-run cable stretching all the way back to the switch, cabling costs are significantly higher. And yes, the central hub itself becomes the new single point of failure. If the switch loses power, the whole network goes down. But the advantages are massive, and they completely outweigh the risks. It's highly scalable.
Adding a new workstation is literally as simple as plugging in a new Cat6 cable. Troubleshooting is incredibly easy because failures are isolated to a single node. And as for that central point of failure, modern switches are built with crazy high redundancy, backup power supplies, duplicate processors, making the risk incredibly low. This is exactly why the star topology dominates modern local area networks today.
All right, we have our roads built. Let's pivot to Section 4, Rules of the Road, and how we prevent digital crashes.
Think about this. Even on the best physical roads, what happens when two devices try to talk on a shared medium at the exact same millisecond? You get a digital crash, a data collision. Enter CSMA CD, which stands for Carrier Sense Multiple Access with Collision Detection. I know, it's a total mouthful, but it is the ultimate traffic cop of early Ethernet. It's a medium access control method. Before a station transmits, it uses carrier sensing, meaning the network card is literally listening for electrical voltage on the copper wire. It waits until no other stations are transmitting, and if a collision does happen while it's transmitting, it detects the voltage spike immediately and just stops.
I absolutely love this. The official documentation literally compares this whole protocol to a dinner party. Imagine a group of guests. Before speaking, everyone politely waits for the current speaker to finish. If two guests start speaking at the exact same time, a collision, they both stop. They wait for a short, random period of time before trying again. Because they both chose a random amount of time to wait, it's highly unlikely they'll try to speak at the exact same millisecond again. It's a brilliantly simple human etiquette rule applied directly to complex digital machinery.
So, what is the exact mathematical procedure when a crash happens? Let's dive into Section 5, Handling Data Collisions.
Here is the split-second algorithmic checklist a device runs in the background. Step 1. Is a frame ready for transmission? If yes, move to Step 2. Is the medium idle? If someone else is talking, wait. If it's quiet, Step 3. Start transmitting, but constantly monitor the wire. Step 4. Did a collision occur? If no, awesome, finish the frame. But if yes, the device immediately drops into the collision recovery procedure. All of these steps happen in fractions of a microsecond, totally invisible to you sitting at the keyboard.
So, the crucial point is what happens next. When the station detects a collision, it stops sending the actual data. Instead, it blasts out a 32-bit jam signal, which is just a pattern of ones and zeros. Think of this jam signal like a digital flare gun going off. It warns everyone else on the network to discard the corrupted, mashed-together data they're currently receiving. Then, the station increments its attempt counter, calculates that random back-off period we talked about at the dinner party, waits, and then tries to re-enter the main procedure to send the data all over again. And the math here is just fascinating. It brings up a concept called slot time. Slot time is essentially an upper limit on how long it takes to acquire the medium, and it dictates the schedule for retransmission. As Ethernet speeds get faster, from 10 megabits per second up to a gigabit, the actual time interval in microseconds drastically shrinks. At 100 megabits, the slot time is just 5.12 microseconds, and at a gigabit, it drops to 4.096 microseconds. That is unimaginably fast. It just proves how incredibly efficient these digital rules of the road have become. The speed limits go way up, but the traffic cops just react faster than ever. But there's a really interesting quirk to this traffic cop system. Let's look at Section 6, the channel capture effect. Because of the way the math works in that random backoff algorithm, a strange phenomenon can happen called the channel capture effect. When two users collide, the one who has collided more times in a row has to pick a random wait time from a larger set of numbers. So if user A collided once and user B collided twice, user A is statistically far more likely to pick a shorter wait time. User A wins the link. If user A has a massive amount of data to send, they might just keep winning that random backoff lottery over and over again. In the real world, this means one person downloading a massive file could literally choke out a coworker's video call simply because their computer keeps winning the mathematical coin toss.
And that brings us to the hard limit, the number 16. 16 is the absolute maximum number of transmission attempts. If user B keeps losing the lottery and colliding, once they hit 16 failed attempts, they abort the transmission entirely. The protocol essentially throws its hands up and says, "We'll try again much later." This creates wasteful idle time on the network, which is exactly when you experience a noticeable lag spike or stare in absolute frustration at a timed-out web page.
Which leaves us with a final, rather provocative thought. As we've learned in this explainer, modern networks are largely moving to star topologies with central switches, not those old hubs. And with modern Ethernet running in full duplex, meaning data can be sent and received simultaneously on completely separate pairs of wire, collisions physically cannot happen anymore. The IEEE standard even deprecated Ethernet repeaters back in 2011. So, as our digital cities evolve into these incredibly fast, switch-based metropolises, are we completely outgrowing the need for traffic hops like CSMA CD? The invisible roads keep upgrading, leaving you to wonder just how fast and how flawless the digital cities of tomorrow are going to be.